9.1 is a turbojet engine. Let's take a look at this problem. An ideal turbojet engine is analyzed using the cold air standard method. Given specific operating conditions, determine the temperature, pressure, and enthalpy at each state and the exit velocity. We're going to use constant specific heats for the cold air standard method, where air at 300 degrees, the specific heat ratio is 1.4 and the gas constant is 0.287 kilojoule per kilogram K. We're given our initial conditions, temperature, pressure, velocity, pressure ratio for the compressor, and then cutoff ratio for the constant pressure heating in the combustion chamber or the heat exchanger. So let's start with drawing the components. We've got a diffuser. My drawing tools here. So I have my diffuser, then my compressor, my heat exchanger, my turbine, which drives my compressor, and finally my nozzle. And I'll label these states 1, 2, 3, 4, 5, and 6. So this comes in at velocity V1, and then throughout the rest of the system slows down to a negligible velocity, and then finally at the end exits at V6. So my diffuser, my nozzle, my turbine, heat exchanger, and compressor. So state 2 is just the finding the temperature at the exit of a diffuser where the velocity is nearly or much, much smaller than the inlet, so we can neglect it. And so using the first law, we would have that T2 equals T1 plus V1 squared over 2CP. And our basic equation for the first law is dECV dt equals Q dot minus W dot, and for one inlet and one exit, we can just have M dot times each inlet minus each exit plus the inlet squared minus the exit squared over 2 plus G C inlet minus C exit. And that would apply to every component in this system. So we'll look at each component separately and evaluate the end states. We're going to make note that this delta H can be replaced with Cp delta T. So that's where we get the temperatures in the equation below. And then we're also noting that there's no significant change in elevation. For the first component, for the diffuser, there's no heat transfer and no work. And in each component, the change in energy of the control volume is not, or is zero with respect to time. So it's a steady state. So that means that change with time, so the derivative of energy with respect to time is zero. Right, and then for the heat exchanger, the work is zero. For the nozzle, the work and heat transfer is zero, the nozzle and the diffuser. And for the compressor and the turbine, the heat transfer is zero. So cross out different terms, but for the nozzle and diffuser, we're crossing out both Q and W. So we end up with delta T plus the change in kinetic. And so 0 equals Cp T inlet, which is T1, minus T exit, which is T2, plus the inlet squared minus the exit squared over 2CP, where we divide the equation by CP. Then we note that the velocity at 2 is much, much less than the velocity at 1, and when we square it, even more so. So we can neglect V2. So we're going to assume that's small, negligible, and that's where we get this equation. Now we do have to use correct units, so we've got 240 K. Well, we're just going to use absolute temperature in the first law. Velocity squared, which is 200 meters per second, and we're squaring that over 2 times the specific heat, and I have so when K equals 1.4 and R equals 0.287, we have that CP equals 1.0045 kilojoule per kilogram K, and CV equals 0.7175. And then again, K equals CP over CV, which would give us 1.4, and R equals CP minus CV, which gives us. So we can put in our value for CP, 1.0045 kilojoule per kilogram. And then we need to the K in there. So we have meter squared per second squared is the same as a joule per kilogram. So another way we could write this, if we don't want to have to multiply or divide by 1,000, we can just write this as joule per kilogram, and then this will be 1004.5 joule per kilogram K. And then meter squared per second squared is the same as a joule per kilogram. So we'll end up with units of K. So we get 240 plus 200 squared over 2009. The temperature of 59.91 Kelvin. Then to find the pressure, we simply use the relationship for an isotropic process relating pressure to temperature. And we have P2 over P1 equals T2 over T1 to the K over K minus 1. For delta S equals a constant, which we're assuming each component is isotropic except for the heat exchanger. The constant specific heat, so CP equals a constant, and also it's an ideal gas. So since those things are all true, we can use this expression, and we just solve for P2. So P2 equals P1 times T2 over T1 to the K over K minus 1. Then to find the specific enthalpy, we'll just use the expression above here. So we have that H2 equals CP times T2, where CP is 1.0045 kilojoule per kilogram K. The temperature at state 3, we're going to use the value given for our P. So that's P3 over P2. And our value for RC is really a specific volume ratio, but it also equals a temperature ratio. So that would just be T4 over T3. So we have that P3 over P2 equals RP. That is equal to T3 over T2 to the K over K minus 1. So we can solve for T3 and we get that T equals T2 times RP to the K minus 1 over K, just with algebra. And some more algebra that actually I'll just already the algebra for P2, but I can write it here. H2 equals Cp times T2. And then of course the pressure at state P2 times RP. And so we'll go on this way through the rest of the problem. I think this gets you started enough. When you get to the turbine, though, sometimes students get stuck with that. I guess just one more thing, as I mentioned, since T4 over T3 is RC, then T4 equals T3 times RC. And then using the ideal gas law, we can get the, we're actually constant pressure process. So P4 equals P3, and the enthalpy we can just get from T4 equal H4 rather equals Cp times T4, where T4 can be found from T3 RC. All right. Actually, I'm a step ahead here. So just erase that. And the enthalpy at state I haven't found yet. So H3 equals Cp T3, and then finally T4 here. Of course, finding the pressure at state 4 is just the same as pressure at state 3. The enthalpy, same way, find the temperature and then get the enthalpy. The temperature at state 5 is maybe the most challenging to remember. It's very simple because the turbine is only there to provide power for the compressor. So the work for the compressor is equal to, we just put the absolute value. So the power output of the turbine is equal to the power input of the compressor. So depending on how we write it, if we write them both as positive values, then we can say that m dot times, actually, if we want to write it as not these, but I'm going to write as Cp delta T. So T3 minus T2 is the work input for the compressor will equal the work output for the turbine. And that would be Cp T4 minus T5. And of course, the m dots cancel, the CP's cancel, and I get equals T4 minus T3 minus T2. And then same way as state 2 to 3, we can use the equation, the turbine's an isentropic process, that P5 over P4 equals T5 over T4 to the K over K minus 1. And then finally, when we get to the end, when we're trying to find the exit velocity, so we have another isentropic process, 5, 6, it will be just the diffuser. So we'll use the same approach. We do know that the exit of the, or at least we're making this assumption that the P6 equals P1. So we're going going to say pressure coming out at the exit is to atmosphere. So it's going to go back to P1. So P6 equals P1. So we can use the expression P6 over P1 equals T6 over T1 to the K over K minus 1. And then we can find T6. And T6, we can use again above here. So we have 0 equals m dot times or delta H, but we're going to put this as CP T going from state 5 to 6, T5 minus CP T6 plus V5 squared minus V6 squared over 2. That's velocities, not volumes. If we divide by m dot, this becomes 1. This is still 0. We can divide by CP. And finally, we get that T6 equals T5. And then we have plus V5 squared minus V6 squared over 2 CP. And like before, V5 is much, much smaller than V6, so we can neglect this in comparison. So it's slow velocity inside the engine, and then it accelerates to high velocity coming out. And so we end up with just 5 V6 squared over 2 CP. And we already found T6 from this relationship, so we solved for T6 there. And then we use T6 to solve for V6. So finally we get V6 equals, and then first we can solve for V6 squared, and then take the square root of both sides. And I'll leave that up to you, just some simple algebra again. I hope you found that helpful. This is also the example problem. So if you want to check your values, you can work through this problem and see if you get the same answers.